I mentioned in which case you can do the exact analysis and approximate analysis for voltage divider bias. As an inverter, you might also see questions regarding logic gates. You can create logic gate with 2 diodes. You can create logic gate with 2 transistors or even more. So understand the operation of logic AND and logic OR. The truth table is given on the right hand side, and see in which case will be there's a high output, or in which case you will have a low output. Once you have determined that you will get some output, you should be able to calculate using the Kirchhoff's voltage law what will be the output. Using the Kirchhoff's voltage law, using the value of the DC supply and value of the resistor. Switching time, shortly we discuss in the class, transistor on and off time. We did not do any analysis using PNP, but if you have any analysis with PNP, the principles are the same, the equations are the same. You just change the direction of the current and reverse the polarity. For AC analysis, we mentioned 3 models in the class, not 2, 3. The small RE model, hybrid equivalent, and hybrid pi. The hybrid pi model, I mentioned the name. We did not discuss it in detail, and it is not part of your course. But the hybrid pi is used in high frequency applications. The common models are small RE and hybrid equivalent. Each has its strengths and weaknesses. We chose the small RE model for all the AC analysis of BJT for this chapter. A model is just an equivalent circuit that represents the behavior of the transistor when it is drawing AC current, it is getting an AC input and providing an AC output. The DC bias is required for the transistor to turn on and power transfer, energy transfer. So again, remember the BJT is a current control device. So in the small RE model, we approximate its behavior using a current source to duplicate the behavior. The small RE model is designed for specific circuit conditions. So if DC level changes, it is quite sensitive. One of the parameters, small RE, you have to find using the equation 26 millivolts divided by IE. That IE comes from DC analysis. The DC analysis will help you to find the base current. From base current, you can find collector, and then you can find the emitter current. So step by step, you have to do DC analysis, then you can find the small RE value. The model approximates on the input side beta times small RE impedance on the input side. On the output side, you have a small impedance R out or RO, small RO. This is when the circuit is not connected. The transistor is not connected to anything. This is the transistor itself in AC behavior. The arrow symbol downwards with the beta IB, that is the IC. It is represented by an equivalent current source. Once you put the main circuit for AC analysis, you have to short the capacitor, kill the DC source by grounding it. The steps are shown. This is same for all types of circuits. Short capacitor, ground the DC source, kill it, and then throw the AC model in the middle. If you now look from the input side, you can see the input impedance. If you look from the output side, you can find the output impedance. The final aim for the AC analysis to find the gain. Voltage gain is V out divided by V in. If you are doing the gain for BJT or even the JFET, you have to know that it is a minus sign because there is a 180-degree relationship, phase difference between input and output. If someone finds a gain with a plus sign, that is not a correct answer. For current gain, BJT, we can define the current gain. There is some current gain equation. This cannot be done using JFET because you know JFET on the input side, it is almost infinity resistance, which is very high impedance. We assume input current IG equals 0. Therefore, the current gain is not defined. It is undefined. There are some cases where you can ignore the small arrow, know about it when small arrow greater than or equal to 10 times RC for the fixed bias, you can ignore it. Otherwise, it is better to take in the calculation. For a voltage divider bias, it is the same. One thing you have to be careful about is when you short the capacitor, one of the resistor gets shorted out here. This is a bypass capacitor. The shorting of the capacitor has an effect which also shorts out the RE. Because of this, for this circuit, there is no RE in the AC model. It is gone. Impedance calculations and gain calculations, they can be done or they can be determined by the same way. No different. Emitter bias, when you do not have a bypass capacitor, the RE, the small RE model looks like this. There are some formulas for this one. I rarely ask this one because it's more complicated. When you connect more amplifier stages with one another, we can call it the cascade system. So you should know some of the basic things. For example, DC analysis is independent between stages. You can do separately. When you do AC analysis, you cannot do separate analysis because during AC, all the capacitors are connected between one stage to the next. The total gain of a multi-stage amplifier is found by the gain of each stage, then you multiply them, just multiply. There's a cascade connection, common emitter, common base for high input impedance. This one will give you a low voltage gain. If you connect two BJTs where the emitter of the first one becomes the base of the second one, this is called the Darlington connection. It's a high current gain amplifier because the two betas, they multiply. The Darlington different currents and voltages can be solved using the KVL equation. I believe it is also given in the formula sheet for Darlington. I'm not quite sure. We taught you current mirror circuit. If you change the current on the input side, you will also change the current on the output side. They will exactly replicate each other. This is using two mirror images or mirror connection of two BJTs. In this case, the equation is not given, but the equation for Ix is VCC minus VBE divided by Rx. I mentioned in the class, so please remember this one to solve any current mirror circuit. There was one homework assignment, I believe. You can create current source with BJT and a Zener diode. This is showing you one example. The total loop current is VZ minus VBE divided by RE. The Zener is fixed, VBE is fixed, therefore the current IE is fixed. When IC approximately same as IE, you have a fixed current source. We call it the constant current source. So the key idea from the BJT is given for some of its behavior. You can go back to the main chapter, chapter 3, in the multiple choice question and also in the main question part. In the multiple choice question, they ask you a lot about concept. That's why you have to study the concept part. For the next chapter, 6, 7, and 8, we talk about another type of transistor. This is still a Three-terminal device, but the construction is different. This is the field effect transistor. Normally we call junction field effect transistor. Most of our discussion is based on JFET. There is another type, MOSFET. There are two types of MOSFET. We studied E MOSFET and D MOSFET. We did not solve mathematical problems from the MOSFET, but there are conceptual things to understand and remember. There are some similarities between BJTs and FETs. The main difference, BJT is a current control device and FET is the voltage control device. You can see from the equation of FET, the equation is ID equals IDSS and then multiplied by, in the bracket, 1 minus VGS divided by VP whole squared. The VGS, get to source voltage, is your input voltage which is controlling. There are three terminals of the BJT: gate, source, and drain. You can have an N channel or a P channel. We don't call PNP or NPN. For JFET, we call N channel and P channel. If you have an N channel, if you're having an N channel, the main structure is built on an N-type substrate, N-type material, and then you have a P-type material wrapping around the N-type. The drain and source, they have separate connections. Gate connection is connected with the P-type material two ends by racking up. The dashed line shows that it goes around. There's a depletion region between P and N-type, P and N-type material. So if you keep the gate source voltage 0, keep increasing the drain to source voltage, what happens? We asked this question in the midterm. The depletion region actually becomes larger. At some point, the channel is closed, which might make you think that the current becomes 0. The current does not become 0. It reaches the maximum level. After that, if you still keep increasing, it keeps maintaining the maximum level. One of the common mistakes you make in the exam is I ask you one thing and you answer a totally different thing. So I believe the question was, in the midterm, the question was, what is the effect on the drain current when the pinch off happens? But many students are trying to describe the effect of voltage. I did not ask you voltage effect, I asked you the current. It is like if I asked you what time did you wake up this morning, maybe you would say 6 a.m., 7 or 8 a.m., but instead you said, oh, I ate bread. I did not ask you that question. Please read the question. Some students, from my experience in the last few years, the experience tells me that some students think if they write anything, they will get the score. This is not my philosophy. You have to answer what is being asked, not something else. I don't want any other story which is not relevant. And then sometimes you are writing the correct answer. Some students, they don't write proper English, but they write in such a way that I can check their knowledge. I will give you full score for that. But sometimes you are saying something which does not make any sense. Not because of the grammar, but you talk about something that is not related. Unfortunately, I cannot give you score for that type of answer. So focus on what is being asked and understand the concept. That will get you more score, or even full score sometimes. We are at chapter, this one. So this was the behavior of JFET, operating region of the JFET. Before the pinch off happens, what happens? The current rises with voltage. This is like a resistor, Ohm's law. It is following the Ohm's law. After the pinch off voltage happens, when the channel is closed, current is at saturation. It is no longer following the Ohm's law. When you make VGS, the gate to source voltage, more negative, what happens? What happens is given in this graph. This was also the question on the midterm. At VGS 0, if you keep increasing the drain source voltage, pinch off happens about at this point. As you decrease the value of the gate source voltage, the pinch off point is shifting. So maybe from 6 volt is 5, 4, 3, 2, etc. And then when you have the VGS equals to the pinch off voltage, there is no current. The pinch off happens early. You will have a lower level of output current. You cannot give unlimited drain to source voltage. The JFET will break down. So when the pinch off doesn't happen, we call this region the voltage control resistor. For P channel, we did not do analysis of the P channel. You can skip this for the exam. You just remember, change the direction of the current and change the polarity. P channel you can skip. This is the symbol of N channel JFET, the arrow from the gate going inside the device. This is the most important equation about the JFET. This is called the JFET characteristic equation, also known as the Shockley equation. I taught you the shortcut way of finding the 4 points on a graph, which will allow you to draw the smooth curve. For an N-channel JFET, which we always took for our analysis and examples, the pinch-off voltage is actually a negative voltage. For a P-channel JFET, Vp will be a positive value. JFET also has its DC and AC analysis. Let's talk about MOSFET for a bit. You just read the theoretical part of the MOSFET. What are the differences? Why you have to be careful about handling the MOSFET, because MOSFET is very sensitive. There is no mathematical thing that you should be worried about from the MOSFET for your exam. Okay. We have the biasing. There are 3 biasing circuits for the JFET, but you need to remember these basic relationships. All FET input current IG is 0 ampere because we assume a very high input impedance. The drain and source current, they are the same. It is the same current flowing through the same channel. It's like the series circuit current. In the series circuit, you have the same current. Shockley equation is applied for JFET and depletion type MOSFET. For enhancement MOSFET, there is another equation. For this one, you can skip it. So understand the fixed bias, what else? Fixed bias, self bias, and voltage divider bias. For a fixed bias, there's a fixed value of VGS, which is minus VGG. You can see from the loop. This is
teacher?
the, yes?
This chapter 7, what do we skip now?
We skip the MOSFET equation.
Okay.
E-type MOSFET. This is the only circuit, biasing circuit of JFET, which can be completely solved mathematically. For the other types, you need graphical solution. For example, self-bias. Here, VGS equals minus IDRS. So you have to draw a graph and find the different value of ID. What is VGS? That has to intersect with your Shockley curve, and then you will find IDQ and VGSQ. Only mathematical problem, only mathematical approach cannot solve this one for the DC analysis. You can see the equations. You have to plot at least 2 points and draw a straight line. For a voltage divider, we also assume IG is 0. So no current is going through here. This one creates a voltage divider connection. VDD R2 divided by R1 plus R2. That's the voltage at VG, point G. The rest you have to solve using the Kirchhoff's law. Input loop, what is VGS? VG minus IDRS. This is a curve. that has a positive coefficient on the x-axis. Find the Q point. The formulas will be given. The different formulas are on the formula sheet if you need to use them. For P channel is the mirror image of N channel. P channel we did not study. Our course was based on N channel. The AC analysis, which is quite important, one of the parameters is transconductance, which connects the output with the input. In this equation, one is the input variable, the other one is output. The output is the ID, input is VGS. The ratio is called transconductance. Delta ID over delta VGS means how much the output current will change when you change the input voltage. The unit is Siemens, capital S. An equation for GM is used frequently. GM equals GMO 1 minus VGS over VP, GM0. And GM0 is 2 IDSS over the absolute value of VP. This equation we use frequently for calculating some gain. Also, when you did, I think, feedback and oscillator circuit, you had to find out GM. Gain without feedback and gain with feedback. For gain without feedback, we have to use GM. Sometimes it's given in the equation, sometimes you might have to calculate and find out. Another parameter is called admittance, YOS. It is 1 over small rd. YOS is also given in Siemens. Sometimes it's found in the data sheet, sometimes it's found on the problem. Instead of small rd, you see YOS, and then it is an admittance parameter. It is 1 over rd, or rd is 1 over YOS. YOS is not transconductance. Even though it's the inverse of resistance, it is not transconductance. Because for transconductance, one of the parameter is output, the other one is input. This one is totally output parameter. The drain source voltage is an output, the current ID is an output. We have an AC equivalent for FET analysis. You see on the input side, gate and source not connected. Because of high input impedance, it is like an open circuit. On the output side, you have the small RD, the output impedance when you don't connect with anything. And then you have a current equivalent GM VGS. This is the same idea. For all AC analysis, you short the capacitor, kill any DC source. Kill means you either ground it or short circuit it. If you short circuit one, this one, for example, it goes to the ground. VDD is killed. From D, RD is going to the ground. And then you put the model in the middle. You can calculate the input and output impedance parameter as well as the gain. What is the voltage gain? This is given in the formula. You can see there is no current gain formula, because if you divide by input current 0, you're going to get infinity gain. It is not defined mathematically. Also, it's a voltage control device, so we are not concerned about the current gain. We are only concerned about the voltage gain. What else? I think they're all the same pretty much. Common source. In all these cases, there's a bypass capacitor. When you do the AC analysis, the source side resistance is gone. If you have unbypassed, it is more complicated. The source resistor is not gone from the circuit, so the formula becomes different. You have to look at the circuit and see if there's a bypass capacitor on the source terminal or not. Then you can use the correct formula. We did op amp. After that, what is the op amp? Do you remember what is the op amp? Can someone describe the main characteristics of an op amp? What is it basically? The op amp will also be a part of your exam. In the final exam, everything from beginning until the end is included. So you have to study the chapters before the midterm. It's a differential amp. Op amp is a differential amplifier. It has two input channels, the inverting and non-inverting, and one output channel. You're looking at a basic differential, but this is the basic op amp. There are three input modes. You can connect single-ended, so you put input on one of the pin, the other one will be grounded. You can have a double-ended or differential. You can put a voltage in the plus pin and minus pin also. The polarity will be different on the input side. So the difference, whatever output you have is the gain multiplied by the differential. AD times VD. VD is V plus minus V minus. Sometimes you can have a common mode input. You connect the exact same input with polarity with a common node involving both the plus and minus pin. This is called a common mode. The common mode voltage VC is V plus V minus divided by 2 multiplied by the common mode gain. You're going to get an output for the common mode. Ideally, the common mode is used to reject any input, means there will be no output, but in real life there is some output. We call it the common mode rejection ratio. This op amp is a very high input impedance in the mega ohm range. Open loop gain is 20,000 or more, like 5 digits. Output impedance is low, less than 100 ohm. The common mode rejection ratio is one of the very important characteristics of op amp. It tells you how good is the op amp in rejecting common mode signal, usually what goes inside a common mode. Not your desired signal, but noise. You want to reject the noise, that's why you should have a high CMRR. This is the output equation of the op amp. The bottom left is the common mode rejection ratio equation. What is the unit of CMRR? If you write like this, what will be the unit for your answer? If you write 20 log AD over AC, what will be the answer? The unit? Who remembers?
Unit of one teacher. Can you repeat that?
Common mode rejection ratio, CMRR.
Was it decibels?
Yes. If you take 20 log of the ratio, the answer must be written in decibels. If you don't write, you get maybe a half or 1 mark cut. If you just take AD over AC, that is a ratio, no unit, but normally we actually express in decibels. So you better put the 20 log 10 multiplier. Some people express only in ratios. There are two types of gain from the op amp. Open loop is large. Once you close the loop with a feedback connection, which means you connect the output with the input using a resistor, most commonly, sometimes with a capacitor and resistor, the gain becomes much lower. The closed loop gain is lower, always, but it improves the stability of the circuit. The gain is less, but you have now larger bandwidth to operate. The response is more linear. It does not distort easily. I taught you inverting and non-inverting op amp and the equation and how to derive them. I showed you in the class. If you haven't taken the note, you can go back to a previous recording. being able to derive the equation is important. And also, I'd like to remind you, when I say derive equation, it means you step by step show how you get the final equation. If you just write the final equation, this is not called deriving, it is called just writing. It is already in the formula sheet. So you don't get the full credit for just writing the equation. You have to show how to derive. This one, what is V out equals minus RF over R1 V in. This is an inverting. If you have a non-inverting, where is non-inverting? Right here. V out is 1 plus RF over R1 whole, and then multiplied by input voltage. In this case, there is no phase shift. You have a plus sign. There are different connections. We studied unity follower when the V out is exactly same as V in. We had the summing amplifier, quite important. If you have multiple inputs coming in the op amp, you can treat each of them as a separate one and then add them. This is the summing inverting op amp. Because of the high input impedance, we can treat them as separate inputs. Then we have integrator. If you have RC, R the first element, C is the second element, you have an integrator operation. Output is minus 1 over RC integral of your input voltage. I think this is a low pass filter, useful in low pass filter, sometimes called Butterworth filter. The high frequency noise will be cut out using the low pass filter. If you have an environment where you have a lot of noise, normally the noise means a lot of vibration, which is high frequency, and it is better to use the low pass. For differentiator, C comes first, R comes later. So it is minus RC dV over dt if the voltage is a time function. This one is the opposite of low pass. This will be the high pass. So low frequency will be cut off, the high frequency will pass. Studied problems like this. I think there was one like this in the midterm. Was there a problem like this in the midterm? The inputs are given, the outputs are given, design the amplifier. But in the midterm, I think I gave you the circuit, and then I asked you to calculate output at different points. I can't remember now.
I think so. I'm
So
not
you
sure.
have different things you're adding. This is you're just adding minus 4, plus of minus 4. It should tell you this is a summing of n. And then inputs are given, the output is given. So you can see one will be a differentiator, the other one will be integrator, and the other one will be just either an inverting or non-inverting, depending on your choice of design. These are simple problems. This is an inverting summing op amp, adding two inputs, gain and slew rate. So this is what happens when you have closed loop. When the open loop, you have a very high gain. But you see the bandwidth is very less. The op amp will not operate in the long range. Once you close the loop, the bandwidth gets increasing, the gain will decrease. Slew rate is the maximum rate at which the op amp can change output without the waveform getting distorted. It is delta V out over delta T, both over microsecond typically. One you should remember, I'm not sure if this is given in the equation sheet or not. Signal frequency is slew rate divided by 2 pi and peak voltage. For the op amp, we have some applications that we studied. If you have multiple stage op amp, determine the gain at each stage by looking at the nature. Is it is inverting op amp or non-inverting? And then you just multiply the gain. You will get the gain of the total stage, the all three stages, all 4 or 5, how many you have. We use op amp to create control voltage source and current sources. In this case, nothing changed in terms of the hardware or the circuit analysis, but just changing the output equation in such a way that you can see one is the controlling input, the other one is the output. For voltage control, voltage source, voltage control, current source, there is nothing complicated. Then you had current control. We are now looking in terms of input current. Also, we are looking at output voltage. Sometimes you look in terms of input current and output current. So the output current is the function of an input current. This one I discussed briefly. This is a very important one. The filter, I would like you to study again the different filters. Low pass, high pass, and band pass. And also their equations are given in the formula sheet, 1/2 pi R1 C1. Which R you will take, which C you will take, you have to decide by looking at which resistor and which capacitor is connected with the input. Then you can know. This is low pass filter, so RC. If you want to further make your curve steeper, you can add a second RC stage. Usually what happens, R1, R2, C1, C2, sometimes they take the same value. For a high pass filter, same case, but for a high pass, C comes first, R comes later. That's the high pass. Equation is the same. When you add a high pass and a low pass, you're gonna get a band pass filter. Individually, you have to calculate for the high pass filter here. This is the high pass. This one will give you the lower cutoff frequency, 1/2 pi R1 C1. And then this is the low pass section, so this will give you the high cutoff frequency. And you have FOL, FOH, using the same equation, but two different resistors and capacitors. If you take low pass first and high pass later, you're gonna get a band stop filter. The output will be like this. Or a band reject filter. Means it rejects a band in the middle. Before that is fine, after that is fine. I told you about the band reject filter during the class. This was up to midterm. After midterm, we studied with power amplifier. We discussed 5 types. What are the types? Class A, B, AB, C, and D. For the small signal amplifier, we just mainly concerned about the gain and linear operation. For high power or large signal amplifier, since power consumption also creates a lot of heat, we are concerned more about efficiency and power capability. For the class A, it will give you an output for the full 360 degree of the input cycle. The Q point will be in the middle of the load line. You know what a load line is. For class B, the output is 180 degree of the input cycle, means it gets only 1/2 cycle. So usually we combine two class B amplifiers in a push-pull configuration. That is the most common one, in order to have full conduction on the output side. The Q point for one piece of class B is at the cutoff point. What is the cutoff point? Maximum voltage, no current. That is the cutoff point. Class AB is a compromise in between A and B. output is more than 180 degree, but less than 360 degree. The operating point is between the midpoint of the load line and cutoff. So you're above the cutoff point, but below the midpoint of the load line. Class C conducts for less than 180 degree. That is the normal case. If you couple the Class C amplifier with a tuned circuit, it can give you full 360 degree output. As long as the frequency, the operating frequency of this amplifier is matching the frequency of the tuned circuit. Otherwise not. Class D is for digital. These are some of the graphs that is showing the output and load and the Q point. Efficiency you can see. A has the maximum conduction but the least amount of efficiency. As you keep increasing the letter, the efficiency goes up. Class C efficiency is not usually defined or used because it is normally used mostly in radio communication circuit, which is not using large amount of power. So efficiency is not given here. What is efficiency? Ratio of output power divided by input power. You have to multiply the ratio by 100, then you get percent efficiency. We studied about different connections. One is the series fed. You notice that it is the symbol of BJT. So in the circuit, if we don't tell it's a power amplifier, there is no way of knowing because there is no special symbol. If you look in the lab at a normal BJT and a power amplifier, the power amplifier will look larger and stronger built because it has to handle a lot of voltage and current. We studied about some equation. For this, I have to warn you that the equation for class A and equation for class B amplifier, they are not the same. If you are asked a question about power amplifier, please read which class is and then use the correct equation from the formula sheet. I will not discuss the equation here today. It is given all on the formula sheet. You can improve the efficiency of class A using a transformer coupling. We did example 12.4 in the textbook, which is the most important one. For this type of case, it will show you different steps of problem solving. So you can jump the efficiency from 25% to about 50% for class A. And we had some equation for class A transformer couple. As you can see, different equations for series fed and transformer coupling. For class B, you always have to use 2 amplifiers, otherwise you're going to get only 1/2 cycle of the output. These are the main equations of a class B amplifier for input power, output power. Sometimes you have to use the current. The current is given in peak value. You have to convert that to DC. In the quiz, most of you did well. I gave you an example of a class B amplifier calculation of input, output power, and efficiency. Maybe more than 90% of the class was able to solve it properly. So your approach was correct. The maximum efficiency equation is a bit different. This is the maximum efficiency. This happens only when the peak load voltage equals to the applied DC bias VCC. Otherwise, you will not get maximum efficiency. So if your question is not about maximum efficiency, or even it is about maximum efficiency, it is safer to use the regular expression. Because if you use the regular expression, later on you can convert to the maximum one. But if you start with the maximum efficiency expression, and the problem is not about maximum, your answer will be wrong. We did all these problems in the class. You can review again. There were some mistakes in the slide. It was saying that one is PNP and the other one is NPN. That is only for the case of quasi-complementary connection, which we did not study. We studied the transformer coupled push-pull. This is both of them are NPN. Both of them are NPN. This slide had a mistake I mentioned to you. This is acting like the full wave rectifier with the center tap transformer. So one side gives you 1/2 cycle, the other transistor gives you another half cycle. So you have a full AC. This was asked in the quiz 2. How or why do you have crossover distortion? I think more than half of the class wrote correctly. For a class B, if two transistors don't turn on and off exactly at the same time, there's a gap in the output voltage, then you have crossover distortion. Class D is for digital. There is a harmonic distortion. Where is the harmonic distortion? I don't see it. Maybe in the next chapter. The next chapter is linear digital ICs. We studied about what? Comparator, analog to digital converter, digital to analog, IC 555 timer, and then we have voltage control oscillator, VCO, phase lock loop. For a comparator, understand how it works. You have two inputs, plus and minus. The output from a comparator is always a square wave. V plus and V minus are not your input voltage. They are a reference voltage level for saturation. There are some cases where you have to build a circuit where V minus is put at ground. V minus I put at 0 volt, V plus maybe plus 5 volt or 10 volt. About 2 weeks ago, I did a personal experiment in the lab using an op-amp, LF411 op-amp, to create a low-pass filter. I have a software in my computer that can act as an oscilloscope. So I was doing that. In that case, I had to put V minus at 0 volt. But this is a basic one. You have inverting and non-inverting op-amp. You can start reading from the non-inverting. The input pin is the non-inverting. V minus is the reference. When V plus voltage is greater than V minus, you will have a high saturation level. If V plus voltage less than V minus, you have a low saturation output, which is minus 12 in this case. If you have an inverting, the input is given on the minus pin. Now you have to see, when input pin is greater than the reference pin, what is going to happen? V minus is greater than V plus. It will go to the negative saturation. So you have to remember by the trick that is the input voltage is given on the plus pin or minus pin. When it's greater than the other one, you have a plus saturation level. Here the input is given at the minus. When this one is greater than this one, you have a minus saturation level. Or you can remember in another way. When V plus greater than V minus, always means V minus is less than V plus. Always you have a positive. When V plus is less than V minus or V minus is greater than V plus, always negative. Kind of confusing, but I think you just choose one of the tricks. We studied about ADC, DAC, digital to analog converter, only one method. We studied the ladder network. So there's a relationship between the vertical resistor and the horizontal. The vertical resistor is 2 times the horizontal one. The first one that is grounded is not this one, which is grounded. It is not considered as a member of the stage. So this is not a 5-stage, this is a 4-stage DAC. D0, D1, D2, D3, and the equation will be like this. You take each input, multiply by 2 power of 0 if there is a 0 input, or you multiply by 2 power if there's an input there. 0 is 2 power 0, 1, 2, 3. It will go like that. This 0 is your input, main input. Divided by 2 power the number of stage and multiply by reference voltage. The voltage resolution is given by reference voltage divided by 2 power n. N is the number of stages. The more stages you have, the more finer voltage you can see when the digital goes from one stage to the next stage. If you do not want to be that much precise, you don't need so many stages. For ADC, we studied 2 methods, dual slope and ladder network conversion. These are descriptive topics, so you can read the description and understand what happens. Same formula for resolution for analog to digital converter. This clock frequency and time conversion formula probably is not given in the formula sheet. So please remember this. Conversion time depends on the clock frequency. 2 power n divided by the frequency. The time you can find in second or millisecond. We studied 555 IC timer. The formula for frequency is given on the formula sheet. There are 2 cases. One is called the stable multi-vibrator, so the output is a repeating square wave. The other one is called the monostable operation. The output is just one short pulse. You just have to trigger it. One of the students, he did the question right in the exam quiz, but he was asking question in his answer that he's not sure whether or not it's triggered. In the equation, in the diagram which was given, the trigger input is not connected. So what I wanted to ask is, assuming that there will be a trigger, how long will be the high output? All of you got it correct, I think, except one student who was trying to tell me RA plus RB. There is no RB in the monostable. There is only one resistor. Output equation for monostable is 1.1 RAC. That is the high time. For VCO, voltage control oscillator, what does it do? It takes an input voltage, gives you an output of certain frequency. There are 2 types of output coming out of the VCO. One is a square wave, the other one is a triangular wave. The square wave comes from the Schmitt trigger. This is the digital part. Schmitt trigger is the digital part. The triangular waveform is developed across this capacitor. It is simulating a charging and discharging behavior. So the output frequency depends on the input voltage. That's why we call it the voltage control oscillator. You can have a fixed value of the output frequency given by this formula. also on the formula sheet. Sometimes you can actually have a potentiometer, a variable resistor in the middle I can put like this. Have a maximum range and a minimum range. We did one example in the class using that one. The most common VCO I see is LM566. The 566 number is the model of the IC. Around it, the numbers are pin numbers, 1, 7, etc. The opposite of VCO is the phase lock loop. It tries to detect an input frequency, and depending on the frequency, it will give you an output voltage, which will be fed back to VCO. The VCO will give an output frequency based on the input voltage. This output from the VCO is compared with the input of the input frequency signal. They might be at the same frequency, but they may not be at the same phase. Maybe there's a phase lag. So for different phase difference, the phase detector will output different voltage level. It is passed through a low pass filter. The output phase detector has two components, a high frequency component and a low one. The amplifier takes only the low frequency component using the low pass filter. The PLL is not a single device. It's like a circuit or a system, which is operating at the frequency 0.3 R1C1, 0.3 divided by R1C1. Three modes of PLL I asked in the quiz: lock, tracking, out of lock. So where is a real example? Also study about lock range and capture range. The lock range is larger than the capture range always, but if you try to calculate, you have to calculate the capture range first. No, the lock range first. The lock range is larger, capture range is smaller. Once you calculate the lock range, you can use this value to capture, to determine the capture range. This is one example. In this example, what is R1, C1? R1 and C1 is here. R2 will be this one. It is not marked R2. This is R2. This is C2. Why do we need R2, C2? To calculate the capture frequency range. It is not a single value. The frequency range that you find, FL or FC, it is not a single value. It is a bandwidth. So from the center operating frequency, you take half of the bandwidth to the right and half of the bandwidth to the left. You will see the actual value of the frequencies, which will let you lock and capture your input signal. Any questions about this one?
I don't have.
Then I will not review 16, 17, which we just studied in the last 1.5 or 2 weeks, but I will quickly discuss chapter 14 and 15. Chapter 14 is about feedback and oscillation, and chapter 15 is power supply. Let's go to the feedback and oscillator chapter. What did we study mainly from the feedback and oscillator? First, we studied with the concept of feedback. What are some of the benefits? The benefits are it will make your gain more stable, higher input impedance, improved response at higher frequency, the operation will be linear, noise will be reduced. What is the drawback, which means the opposite of benefit? The drawback is the gain will be less. I think we can live with it. There is no point in having a 1,000 or 20,000 gain if you cannot control it. It's like having a very high performance car. Maybe it runs 300 kilometers an hour, but can you control it in a normal road? You cannot. So that's one analogy or comparison. The basic equation, we derived so many equations here. In this case, you see you have an input signal Vs, it is not Vi. And then this is a mixer network. The mixer network gets the input signal Vs minus the feedback signal Vf. The difference between Vs minus Vf is Vi. This Vi goes through an amplifier. If there is no error, there will be no feedback signal here. Vs equals Vi, but normally there is an error. So based on the error, it will actually try to correct. This is amplified given at the output. The gain of the overall loop is V out divided by Vs. Gain with feedback. And gain without feedback is, gain with feedback is much less than gain without feedback. The generic equation is A divided by 1 plus beta A. A is the amplifier stage. A is right here. Beta is the amplifying factor of the feedback element. This is conceptual building block. Then we studied how to use actual elements to build these networks. This is one of the actual examples using a JFET and resistors, voltage series feedback. You see the part of the output is fed back onto the input side. This is minus V out R2 divided by R1 plus R2. Beta is minus R2 divided by R1 plus R2. Why? Because beta is, what is VF? VF is beta times V out. Derive this. I asked this problem in the class or quiz 2. Most of you did it correctly. Most of you did not say, AF is 1 over beta, because A was not much greater than 1. A was, I think, minus 30 or minus 28 in your problem, which is not 1,000 or 10,000. So you did it correctly. And beta was minus 0.2. Gain with feedback you found about minus 4, I think, which was also a correct answer. I think I asked this question. I'm not sure. Or I changed the GM value. You can also use other types of voltage series feedback. This one is an op-amp using 2 resistors. In this case, you see the input is given on the plus pin. Your beta is a plus value. VF is V out R2 divided by R1 plus R2. Straightforward equations. It says calculate the voltage gain of the circuit. It is asking you to find the gain with feedback. So AF equals A divided by 1 plus beta A, remember, and then beta you can find. You are given A, you can find the gain with feedback. We talked about some distortion, noise, and nonlinear. What happens to bandwidth when you give a feedback? Gain stability. You can skip 13, 14, and 15. Slide 13, 14, 15, 16. I do not discuss about Nyquist frequency or Bode plot. This is the topic of another subject. Although I discussed briefly what is a Nyquist plot or Nyquist frequency. 13 until 16 you can skip for the exam. about oscillator operation, the overall feedback signal has to be positive. If you don't have an overall positive feedback signal, overall, or you have a gain less than 1, the oscillation will die. So you will have some oscillation in the beginning, after that it will die, there will be no output. If the overall gain is greater than 1, the oscillation will keep happening. At some point it will be saturated, which is all right, it's a steady state. Using this concept, we can manipulate the different components of the feedback loop to have oscillator. We can use the fundamentals of the feedback loop to create oscillator, which will give us regular periodic waveform. So that is being used in many of these oscillators. First one is the phase shift. In the phase shift oscillator, the output of the amplifier is connected to a network of RC stages. The phase shift from the RC network is 180 degree. It doesn't mean that each stage is 60 degree. Each stage may not be equally the same, but the overall phase shift is 60 degree. Equation is given on the formula sheet for the phase shift oscillator. 1/2 pi RC square root of 6. This is a block diagram, but you can see in a regular component, a JFET amplifier, the output is taken from drain, and then you have a feedback network with 3 resistors and 3 capacitors. If you connect like this, you will have an oscillation that keeps going on forever. Now, tell me, what is the overall feedback of this circuit? Is it positive or negative? I'm trying to test your concept.
Can you repeat the question?
In this circuit, the overall feedback, is it positive or negative feedback? The overall feedback.
They're positive.
Positive. Can you tell me the reason for that? Your answer is right. What reasoning did you use? What is your reasoning for that?
Because they have like more resistor and capacitor.
Is that a good reasoning? Can anyone else tell me? Okay, first of all, JFET, what is the relationship of input and output? What is the phase shift? What is the phase shift of a JFET?
180 degrees.
180 degree. Okay, if 180 degree, let me put a positive input here. What is the output from the terminal D? It will be phase shifted 180 degree, right? Negative. What is the phase shift in this network, RC network? 180 degree, another 180 degree. Negative and another 180 degree, negative and negative. When you come out of this, it will be positive. This part is the 180 degree shift again. So you shifted by 180 degree in the beginning. Part of the output is fed back another 180 degree. Right now you have a 360 degree flip. Means you come back to the same phase. So overall is positive. That's why the oscillation is going on. Remember, for the oscillation to keep going on, the overall feedback has to be positive. If gain less than 1, the oscillation will die as well. If the feedback is negative, the oscillation will also die. If gain more than 1, the oscillation will keep increasing until it saturates. This is another practical example using an op-amp. You know the input is given at inverting pin. So whatever is coming out is phase shifted 180 degree, and then it is passing through what? Another 180, so you're gonna get plus. Originally, you have to start with plus. You have, let's say you give a plus voltage. This, you're getting a minus. After you pass through the stage, the RC stage, you have plus. You come back to the same polarity as the original signal, then you have a positive feedback. Equation remains the same, 1 over 2 pi RC square root of 6. Straightforward problems, just plugging in the equation. This one we did in the class. We actually did a design problem. We wanted the value of C such that F equals 1 kilohertz, and we needed to find the value of RD for A greater than 29. Why A has to be greater than 29? This is not part of your course, but it is done using a classic network analysis theory. BA, I think it's 29. Beta times A must be 29, and overall loop gain, beta A, greater than 29 in order to ensure oscillator operation. That's why. Another one is Wien bridge oscillator, using 4 resistors and 2 capacitors in a bridge connection and applying to an amplifier. Different equation. In the formula sheet, it is there. There are two things happening here, phase shifting and feedback. The phase shift components will be the one which are connected with a capacitor. So R1, C1 and R2, C2. And then R3 and R4, they are not directly with the capacitor in the same branch or in a loop. R3 and R4 are used for feedback. So two things happening, feedback and phase shift. You have an oscillator. This is another way of drawing a Wien bridge oscillator. See, in the equation has only R1, R2, C1, C2. There is no R3 and R4. In order to connect the frequency of the oscillation, we don't use the feedback resistor value. We use only the phase shift resistors and capacitor value. We studied about tuned oscillator, which is also known as LC tank or LC resonant. You can create a parallel combination of inductor and capacitor. Sometimes we have 2 capacitor, 1 inductor. We call it the Colpitts oscillator. 1 over 2 pi square root of LC. Sometimes you find equivalent C, sometimes you find equivalent L. Equivalent L is for what? Hartley. Colpitts is 2 capacitor, 1 inductor. Hartley is 2 inductor, 1 capacitor. Or you can have 1 inductor with the center tap transformer, which makes equivalent of 2 inductors, which is this one. This part is the tank circuit. You have to find total L by adding them, and then by adding 2 times a coupling factor. This one was asked in the quiz, I believe. Many of you got it wrong. Maybe you pressed the wrong calculator button. We talked about crystal oscillators not in terms of mathematics, but mostly conceptual. You can go back to that lecture and listen again. What I talked about crystal, it has 2 frequencies, series and parallel resonant frequency. In one frequency, it has low impedance, and the other frequency, it has high impedance. This is how you connect a crystal in a circuit. And then this is the symbol of crystal. this one. When it is connected in series, low impedance, only this part determines the resonant frequency. This is a series connection in a loop. This one is a series connection in a loop. Connect in parallel. When you connect in parallel, these three components will determine the resonant frequency. In this case, you see the crystal is parallel with respect to the rest of the circuit. This one is a high impedance operation. Unijunction, I mentioned only a little bit about it. What is eta is between 0.4 and 0.6 is the rating of the transistor. For different material or alloy. For alloy, I think it's 0.5 for eta. If you take 0.5, the equation becomes a simplified equation. So this is that from feedback oscillator. The last one is power supply. I'll quickly go through. We have a few minutes left. The basic idea of a power supply. You get power from the main line, which is 110 volt in abroad, some Western countries, 110. Here we have 220 volt RMS. Step down transformer will decrease the voltage so that the rectifier, usually a diode rectifier, can handle it. You need a full wave rectifier to give you output like this for 180, so you have 360 degree. But this is not the final destination. The final destination is here. This DC is what you want to get. In order to reduce the peak, we have to use a filter. Normally a capacitor filter, if you pass through a capacitor filter, it will give you a waveform like this. This is charging, discharging, charging, discharging, but still it's not a straight line. You can further add another stage, which we did, RC. It will become less ripple, but nonetheless the line is not straight. Then if you put an IC voltage regulator from the filter circuit, you're going to get a straight line, which will be delivered to your load. A good power supply regulates the voltage in such a way that if there is a disturbance on the source side, or if there's a problem at the load side, it will still try to keep you the constant output voltage. That's a good power supply. You can read about each stage. One of the factors is called ripple factor. V ripple in RMS divided by VDC multiplied by 100. If it is a small number, it's better. If it is a large number, means you need a better filtering operation. There are some equations here which compares the ripple factor of half wave and full wave rectifier. For a capacitor filter, there are some equations. We have a word of caution here. In this equation, RL already in kilo ohm, C in already in microfarad, I already in milliampere. So if you have this type of equation, you have to keep that in mind. The larger the value of capacitor, the better the action of filtering, which means the ripple will be less. But if you try to do that, remember from this equation, if you increase the capacitance, you will also increase the current that will pass through the diode rectifier before. You can burn the diode if you do not follow the maximum current rating. Another topic we talked about is RC filter, which is additional filtering, and voltage regulation, percent voltage regulation, V no load minus V full load divided by V full load 100%. It means how much the output voltage can vary when you connect a load to the source. Normally what happens, if you have a voltage source, the two terminals, if you do not connect them, it doesn't draw current. You can measure the terminal voltage using a voltmeter. Maybe it is 60 volt. Now you connect with the load the load starts drawing current from the source. If you measure the output now, it becomes 56. So this is the parameter that shows what happens when you add a load to your source voltage. That's the percent voltage regulation. The less the drop, the better it is. We had some series discrete elements to create voltage regulator. I asked one of these type of questions in the quiz, maybe also important for the exam. So review these concepts again. In this case, V out is Vz minus VBE. Another case, you have Zener with 2 transistors. We have voltage regulation using op-amp and BJT. This V out equation is derived using the voltage divider and the fact that V plus equals V minus for the op-amp. If you forget the equation or if it's not given, you can still derive it. On one side, you see V plus is Vz and V minus is V out R2 over R1 plus R2. That's voltage divider. For a current limiter, we explained this one. Shunt, we also explained what happened shunt. I think this one was in the quiz. Shunt voltage regulator, was it? I asked this one in the quiz. What is output voltage? Vz plus VBE. Input current, V in minus V out over Rs. That's the input current. Output current will be V out over RL. It's not that complicated. This is the problem that I asked. Example 15.11. And the output equation is given for the shunt voltage using 1 Zener and 2 transistors. This is the improved shunt operation. We have an IC voltage regulator. Depending on the series, this is 7812, so it will give you 12 volt output. But in order to operate, each IC needs at least a minimum operating voltage. We can create adjustable voltage regulator using another IC named LM317. So there's nothing else from the power supply. Your final exam, I will tell you on Friday, March 18 from 1 p.m. until 4 p.m. I created the calendar event. It should show on your Microsoft Teams now. Try to log in maybe 10-15 minutes earlier so that we can do all the attendance check. There are 2 parts, 20 multiple choice, I think, in the first part, and in the second part you have 9 written questions. You will get 3 hours, which should be sufficient for the exam. I'll now do the attendance call for all of you. Mr. Balan.
Present, sir.
Present. Tiravut.
Yes, sir.
Napatra.
Yes.
Pakon.
Yes.
Rajay.
Yes, John.
Jonikan.
Yes,ค่ะ.
Michelle.
Yes,ค่ะ.
Phil.
Here, sir.
Silicon.
Yes.
Wisalut.
Yes, sir.
Yucheng. Mr.
Yes,
Yucheng
yes,
present.
sure. Yes, I'm
Chesihan.
present.
Yes,
Yeah.
John.
Patompong.
Yeah, how?
Kongsu.
Yes, John.
Martin.
Yes, John.
Kolawit. Pichayut.
พิชยุทธครับ
Okay. Jimma.
Yes, sir.
Sonwan,
Yes.
Satawat,
Yes.
Yapeng. Yapeng.
Yes, teacher.
Okay. Seni,
Yes, present.
Sidipok,
Present.
Pitu,
Yes.
San'an, Waramet,
Yes.
Navawan,
Present.
Natapop,
Yes, present.
Warapat,
Present.
Nataya,
Yes, teacher.
Pichayapon, Komchan,
Yes.
Piladon, Kitsanapong,
I'm here, teacher.
Atitya,
Present.
Tasin,
Yes.
Sukaina,
Yes.
Sirin,
Yes, teacher.
Min Luin U. Min Luin U is absent. Okay. See you during the exam time. Good luck for your final exam.
Thank you.
Thank you,
I
sir.
hope all of you will not repeat with me again. I don't want to keep my student forever. You will be fine. Just in the exam, do not rush. Read the question carefully. You will be fine.
Thank you, John.
Okay, welcome.
Thank you.
Thank you, teacher.
Teacher,
Yes,
do you check my attendance?
your name?
You Chen.
Yeah, I checked. You Cheng.
Okay, thank you, teacher. See you on
Okay.
exam day.
See you at the exam. Bye.
Thank you, teacher.